CEO and founder of Everlaw, AJ Shankar.
Right. Hello, everybody. Welcome to the final day of Everlaw Summit. I'd like to kick things off with a chat about generative AI, the technology that's taken everybody by storm. GenAI is here to stay. I've seen a lot of technology hype cycles, but this is the real deal. To begin, I'll talk about how GenAI works, and then I'll talk about how Everlaw is approaching this technology for best use in the legal space, and show you some of the features we've released in the beta. And finally, I'll close out by discussing these features with one of our beta customers. Now, I could just jump into this snazzy demo, but I think it's really valuable to start by explaining how GenAI works for a few reasons. First, because you're a practitioner. Knowing how GenAI works, even behind the scenes in Everlaw, allows you to appreciate its strengths and weaknesses better and ultimately derive more value from it. Second, as an educator, this knowledge gives you the opportunity to educate your own stakeholders and clients about a topic that's on everybody's minds, and to show them that you know how to get value from this innovative technology in a responsible way. Third, look, you're going to see GenAI elsewhere in your career and in your personal life, and I hope some of the knowledge you gained today is useful in those venues as well. And finally, purely for your own edification, these kinds of innovations come along only so often, and I hope it's useful to you just as a person, observing societal change, to demystify the magic a bit. So let's dig in. Let's start with machine learning, the general class of technologies that GenAI falls under. Machine learning is the most widely applied form of artificial intelligence. So what is it exactly? Let's think about a calculator, okay? So a calculator simply performs the fixed functions it's programmed to do, addition and subtraction and so on. It doesn't change its result the more you use it. It's reliably the same every time. That's actually what you want for a calculator, right? As a result, a calculator can be created with a simple fixed algorithm in code. But now imagine that the task is to coach a sports team. You don't want a rigid approach, right? To coach a team, you want a system that learns from how different players perform together, what your competition is doing, and so on, right? So that synthesizes new information coming in and updates its behaviors accordingly. So a coach who has exactly the same playbook at the end of the year as she did at the beginning of the year is probably not going to do as well as one who adapts her playbook as the season goes on. Now, machine learning systems are like a good sports coach. They perform better by adapting when given more data. So one of the challenges here is you can't just create a machine learning algorithm from fixed code, right? It has to adapt and change over time in a way that code can't. So instead, you use code to create a statistical model, which is basically just a bunch of numbers chained together like a spreadsheet. And that model is what changes over time to reflect the latest learnings. The model is what you consult for answers, not the code that created it. So get used to thinking about the model rather than the algorithm. There isn't one. Now, conducting an investigation or running a litigation is much more like coaching a sports team than it is like operating a calculator. The issue at hand and the specific documents you review will impact how you spend your time. That's why many of our innovative AI features like predictive coding and clustering use machine learning-based approaches. Now let's talk about generative AI. GenAI is a form of machine learning. The main difference from these other AI techniques that we've used is that it can also, generate output that we as humans can easily consume. Now, there are lots of kinds of generative AI. Some create music, some create art. The area of generative AI that's most relevant to us today are large language models, or LLMs. LLMs deal in text. They can read and write natural languages like English. So if you've used ChatGPT, you've used one. Now, this capability opens up a whole new world of use cases, especially in the law, right? Since so much work is done in natural language. So let's start with some history. Where did this breakthrough technology come from? It turns out that LLMs are based on some very well-established technologies, but also recent developments have completely changed their trajectory. LLMs are all neural networks, which are over 50 years old, actually. Their models, those statistical spreadsheets of numbers, are built on a network, which has nodes and edges. It's called a neural network because it's similar to your brain with its neurons and axons. Information flows along the edges from node to node, with computation happening along the way. Now, again, think model, not algorithm. The intelligence is really embedded in this network, not in any particular code. So in the 80s and 90s, improved training algorithms increased support for networks with many layers, so-called deep neural networks. But they weren't ready yet. It takes a lot of computational power and a lot of training data to make a deep neural network useful. And back then, neither compute nor data was readily available in the requisite amounts. So even though neural nets had tons of potential, there was no way to realize it. But in the 2000s, shifts in these two major requirements set the stage for LLMs. OK, who here has played Quake? Yes, yes, I'm one of these people. OK, great. If you did, you contributed to the existence of LLMs by helping drive demand for a novel source of computing power. So the advent of games with 3D graphics in the 90s and beyond, yes, starting with games like Quake, drove demand for specialized graphics processing units, or GPUs, to supplement CPUs. These are the chips that make amazing graphics on your Xbox or PC. Now, interestingly, GPUs are extremely well suited for training neural networks, much more so than CPUs. So suddenly, and especially in the 2000s, massive computing power was available thanks to GPUs. They're now the backbone of nearly all GenAI endeavors. So thank you, PC gamers. Thanks, teenage me, also, for this technology. Now, second, in the 2000s as well, the adoption of the internet led to orders of magnitude more available training data, right? The written word is everywhere on the internet, from social media to Wikipedia. And so natural language training data to the tune of hundreds of billions of words was now available. Still, there was more work to be done. And the 2010s delivered some key algorithmic improvements. The first major innovation came with inventing a better way to understand the meanings of words in relation to each other. Historically, machine learning algorithms would treat words as separate entities with no particular relationship to each other. But that's not how we as humans think of words. The meaning of some words are closer to each other than others, right? So happy and glad are closer than, say, glad and mad, even though happy and glad don't look anything alike. Or consider words with complex meanings that we can tease apart and then relate. We might recognize that king and queen differ by gender, but are otherwise similar. So these kinds of relationships are important when trying to determine the meaning of a sentence, right? Considering words in a vacuum just wasn't cutting it. And so what happened is this new technique of word embeddings came along, which really took off in the 2010s. It moved from representing words as just the ordering of their letters to a much deeper representation of meaning by encoding each word into hundreds of numbers that essentially encompass what that word truly means. Now, each of those numbers has no particular meaning in itself, but together they're really powerful. Using numbers allows models to discover relationships between similar words using math. Even if their letters aren't related at all, their numerical embeddings will be. For instance, plotting the word embeddings, the numbers for mad and happy and glad, immediately shows the relationship between these words. Happy and glad are close together, and mad is far away. Furthermore, because you're dealing with numbers, you can actually do math on these embeddings to discover even more relationships. So for instance, you can take the embedding for king and subtract, and yes, I mean actually subtract, right, the embedding for man, and add the embedding for woman, and the resulting embedding will get you queen. With embeddings, LLMs can operate on the underlying meanings of words. Focusing on meaning allows them to be much more expressive and powerful. Now, the second big algorithmic improvement was on better understanding the meanings of words in context. The breakthrough here is called a transformer. And it provides a way for an LLM to focus its attention in the right place to understand what a word means. Take the sentences, the mouse nibbled on the carrot because it was hungry, and the mouse nibbled on the carrot because it was yummy. Now, what does it refer to in each sentence? Well, we know that it's the mouse and not the carrot in the first sentence, and vice versa for the second sentence. But an AI from a decade ago might not have figured that out. But with transformers, they now can. Transformers are a way of extracting the right meaning and context reliably and efficiently, which is essential for fluent communication. Finally, as we hit the 2020s, a few more pieces fell into place. With lots of compute and training data, it was now possible to build really large models for the first time, and some startling results emerged. When models like GPT-3 surpassed 50 billion parameters, researchers saw surprising emergent properties, for instance, dramatically better fluency. As it happens, a certain amount of scale seems necessary for intelligence. And as soon as researchers saw performance picking up, they invested heavily in scaling up model size further. You can see that these model sizes have exploded in the past 3 years. Humans were the final change that allowed this AI renaissance to occur by moving beyond just automated training. Surprisingly, putting humans back into the loop makes a huge difference. For the highest performing systems, after standard training, humans provide reinforcement by giving feedback on good and bad answers. The LLM learns from this feedback and to give substantially better answers than it might otherwise do. Okay, so here are some takeaways from that brief review. So first of all, ChatGPT and its ilk were not overnight discoveries. There is a long history of research and innovation behind them, stretching back decades. This research set the stage for algorithmic innovations in the last 10 years that have unlocked the potential of large language models. Second, a confluence of factors from other areas of computing, like GPUs and the internet, were also essential to the development of large language models. Okay, finally, you should expect even more rapid change from here on out. Thousands and thousands of researchers are studying AI, and the rate of innovation is only increasing. Look at the number of papers published by one of the leading conferences in the area. This is not an exponential graph of compute power or network size. It is a graph of human effort. So get excited about everything that's yet to come. By the way, did you know what GPT stands for? GPT stands for Generative Pre-trained Transformer. Generative because it generates output. Pre-trained because it gets trained on broad swaths of natural language, not on your specific task. That pre-training is actually sufficient to enable all kinds of use cases without further domain-specific training, which is pretty remarkable. And transformer, because as you now know, it uses transformers to pay attention to the right parts of the text. That's all, GPT. I hope this comes in handy at your next bar trivia night. Okay, so that's the history. How do these things actually work? There are two big parts, training and inference. Training is how a GenAI system learns, and inference is what it does to generate words when you're interacting with it. Note that unlike a human brain, these two parts, training and inference, are disconnected. Inference is read-only. So when people talk about ChatGPT learning from chats, that's typically going to happen during a subsequent explicit training step, not during the live chat interaction itself. Okay, so training. How does an LLM go from nothing to fluency in natural language? Simple. It learns by example. You feed it examples of natural language, like English sentences. Lots and lots of examples. Billions to trillions of examples. As we discussed, that means things like social media and Wikipedia and so on. Now, the essence of the training process is actually quite straightforward. Feed the LLM a sentence, but blank out one word. Then ask it to guess what word goes in the blank. It'll use word embeddings and transformers to analyze the sentence and the neural network it's building to hazard a guess. So, for example, if a sentence in the training data is the sky is blue, feed the LLM blank sky is blue, and then feed it the blank is blue, and so on. Each time, the model will make a guess about that blank. Now, if it guesses right, okay, great, move on. But if it guesses wrong, and this is the critical part, it walks back up its network and figures out how to update its model to make it a bit more likely to guess the right answer next time. This step of learning by guessing and correcting is the absolute heart of large language models. Now, if you do this across tens of billions of sentences, the model learns natural language. Eventually, its guesses get so good that you can start using it. What's wild is you don't need to feed it, explanations of different languages or syntax or grammar. It infers all of those things from the training process. It just learns by filling in the blank over and over. And by the way, hopefully it's clear now why it's helpful to have lots of training data and also lots of computational power to run this process on. I do want to take a moment to appreciate the human component in this endeavor. There is a lot of art in making these networks. They require highly skilled engineers. The parameters get filled in via training, but the structure is determined by people. Humans need to decide on the size of the network, right? The number of neurons, the number of layers, the function of the layers, the order of the layers, the activation and normalization functions. That's the math that allows the computations to flow across the network. The embedding approach, right? How do you actually convert words to numbers? What data to train on? How do you correct mistakes? And many other things. So there's a lot of expertise that has to be brought to bear. But once these decisions are made, it does come down to training. The training process yields some remarkable results. After being fed billions of sentences, modern large language models have many competencies. And here are the 4 that I think are most important. First of all, fluency. Fluency in natural language. They can read and write in English and other languages with better grammar than most of us. That's, in itself, I think, pretty amazing. Number 2, creativity. Analogies, new concepts, stories, poetry, and more. And not just regurgitations or remixes, as some people claim, but actually truly novel connections and ideas. Number 3, knowledge, embedded knowledge. LLMs don't just infer the rules of grammar and language from those billions of sentences. They also internalize all the knowledge contained within them. Remember, they're fed all of Wikipedia and much more. And the act of filling in the blank for each word means that they're building statistical representations of all of it. So embedded in the model is a huge amount of knowledge. And finally, logical reasoning. They can, to an extent, make inferences and connect the dots. This is probably the most surprising emergent component. I'm not sure that the early researchers really expected this. If you're one of the folks that believes that the development of language was key to unlocking our own cognitive abilities way back when, follow these AIs closely. Now, this is a lot of bang for your buck when it comes to training, and we'll revisit these competencies in a bit, so stay tuned. Okay, so that's how you train an LLM. How does it actually produce output, the inference part? Well, in almost the same way as they train, by filling in the blank. But this time, the blank is at the end of the sentence, so it's really just predicting the next word over and over again. Let's go back to our sky is blue example. Let's say I ask an LLM, what color is the sky? Behind the scenes, the machinery gets to work. The LLM converts those words to numerical embeddings to better capture their meaning, and the transformers figure out where to focus attention. So in this case, the word color will be the focus for an answer to the what question. That's why it's going to most likely guess a color rather than another descriptor like, overcast. So then it makes a guess, just as in training. What word comes next? Except this time, it's fully trained, and its guesses are good. It starts outputting words one at a time, building on whatever it's already outputted, right? So the sky is blue. OK, how does it know that? Well, we're talking about massive scale here, with the LLM trained on billions of sentences. Enough of these sentences contain essentially the notion that the sky is blue, that the LLM statistically suggests blue as the right continuation for that sentence. Recall, though, that I said the LLMs are models, not algorithms. There is nothing to consult to understand why it said the sky was blue. It has no database of facts that say the sky is blue. It has no reasoning about why scientifically skies are blue. It is just predicting words. This is critically important to understand. These models know the frequency of words in context. They don't know what is right or wrong. There is no notion of understanding. There is no deeper explanation. Even if you ask one to explain its reasoning, it'll generate that explanation in exactly the same predict the next word way. It can't truly introspect. And yet, the outputs can be tremendously impressive. Any of you who have played around with ChatGPT knows what I'm talking about. But how, right? How can it be so good without understanding anything? I find intuition is the right metaphor to use to appreciate what's going on here. If you think about how you develop intuition, it's by getting lots of practice with something. And as you do so, behind the scenes, your brain synthesizes that information so that you can put it to use automatically. Think about jazz musicians who have played so much music that they can improvise in real time on intuition alone. Or chess grandmasters playing blitz chess, okay, with time limits of minutes rather than hours. They don't have time to evaluate every position consciously. But because they've played thousands of games of chess already, their intuition is so good that they can still play extremely well without that deeper analysis. Or athletes who have done so many reps that they actually often perform best in the moment without conscious thought. Or even how you've driven a car enough that you can drive without much effort while listening to a podcast, right? That's basically what these LLMs are, the world's best intuition machines. Their practice is being trained on billions of words of human writing. In building their models during training, they're synthesizing the collective written works of humankind. It just turns out that that synthesis is extremely valuable in itself. They've developed an intuition about human knowledge and expression and can produce meaningful outputs without any deeper understanding as a result. So keep that in mind. You have the world's most comprehensive intuition at your fingertips. Now, there's another fascinating aspect at work here as well. Remember that second competency, creativity? If you've played around with these tools, you've likely been surprised by how creative they can be. How can something that just predicts the next word be so creative? Isn't that a uniquely human trait? Well, here's a blunt truth. Creativity isn't that magical. Creativity is randomness plus taste. Now, sorry, that's not some kind of scientific formula. I made it up myself. But I think it's true. Creativity requires making something new. That's the randomness part. And then being able to tell the good from the bad, so you only keep the good stuff in. That's taste. That's really all there is to it. LLMs are really well on their way in both fronts, randomness and taste. Now, on the randomness side, consider that when the LLM predicts the next word during inference, it doesn't have to pick the most likely word. It could choose a random one amongst the top several most likely words. You can actually control that variable. It's called temperature when you use an LLM. The fascinating thing is that studies show that LLMs produce better output as measured by actual humans when they don't always pick the most likely word and instead roll the dice amongst the top several words. That's the value of creativity in action. Now, as far as taste goes, well, in a sense, they have the statistical average taste of their training data. And it turns out it's not terrible, and sometimes it's pretty good. But you can definitely create LLMs which favor particular kinds of taste. And I would expect research in this area to yield even better creative output in the future. So in short, LLMs can be creative. Strike one more thing off the list of things that humans are supposedly uniquely good at. OK, so we've covered what LLMs are, some history, how they work, and even a bit of what they're capable of. I hope that's been a worthwhile tour for you. I also think it's essential education at this point to think about how to use GenAI. GenAI is a powerful transformative tool, but as with any tool, it can be used well or poorly. So at this point, I do want to transition the talk to focus on how Everlaw embeds the usage of GenAI into the platform experience, based on our AI principles and our knowledge of legal use cases. We want to make sure that you, as Everlaw clients, both use GenAI well and also understand how we're enabling that usage for your own edification, and also so that you can educate your clients and stakeholders about it should they ask. Now, back in June, we published our responsible AI principles that were aligned to our overall company philosophy about building our platform. I want to cover those here. Now, most importantly, our philosophy at Everlaw is to build for the long term. We're not trying to make a quick buck. We're trying to change the way a whole industry works for the better. This is going to take a while, and we should act accordingly. Now, how can we achieve these long-term outcomes? By acting with integrity and with discipline. Integrity means doing the right thing when faced with a tough decision. We should make the right call rather than, even if it's not the easy call, right? And discipline is doing things the right way. We don't cut corners or waver in our commitments. So this is actually our core company philosophy. Every candidate we give a job offer to learns about this along with their offer terms so that they can align on this point of view before they accept. And we've applied the same mindset to how we've approached AI. We're much less interested in being first than we are in being best. Now, don't worry, this doesn't mean we're going to be last either, far from it. But it means that the quality of the experience and the mitigation of risks is key. Here are some of the GenAI principles that are motivated by this point of view. First, we put you in control. You choose if you want to opt in or opt out of using GenAI. You'll know which foundational models we're using. And when you use our AI features, you'll always know that you're interacting with AI via a visual cue. Second, we focus on privacy and security. So consistent with our strong security culture, if we use any third-party AI tool, our legal and security teams will evaluate the specific system's operational approach, the data that will be processed, and the safeguards that are in place to protect the data, and review the governing legal terms to align with our commitments to you. Furthermore, we're only going to select third-party GenAI tools that do not train their models on your data. And finally, since we started using OpenAI as an LLM partner, we've been working to ensure the privacy of your data. And I'm pleased to announce that any data passed from Everlaw to OpenAI has zero data retention. Zero data retention means that when your data is sent to OpenAI, they can't store the data. They can use it to process the task at hand, and then they have to remove it. Now, the third and hardest bit is confidence. Generative AIs can provide immense value, but they can also make mistakes. We all know about the potential for so-called hallucinations. We want to ensure that users can develop confidence in the usage of GenAI on Everlaw so that they can get the most value out of it. Now, how do we instill confidence? First, by building our features to utilize the strengths and avoid the weaknesses of generative AI so that results are more likely to be right. Second, by making it easier for you to check the AI's work. Let's go into those in more detail. So the question to ask here is about LLMs as a category of technology. How do we ensure that we're accounting for their strengths and weaknesses, especially as applied to the law? Well, what do I mean by this? Let's revisit the four competencies, the core competencies of LLMs, right? They have fluency in natural language, creativity, embedded knowledge, and logical reasoning. We can examine these competencies to guide our usage. For starters, natural language fluency is a key strength in our domain. Discovery is so dependent on the written word, and fluency here is essential for our core workflows. Same goes for logical reasoning. Plenty of dots to connect in our space. It gets more interesting with creativity and knowledge. Varying amounts of creativity are useful in litigation and investigation, depending on the use case. Sometimes you want to be really buttoned up. Other times you need to be able to think a little bit outside the box to figure out what's going on, and creativity can help there. Finally, embedded knowledge, which is probably the most commonly used competency for lay people. Let's explore that one a bit. So you might ask ChatGPT about the 1990s bulls or things to do while visiting San Francisco on vacation. Now, recall what you've learned about large language models during this talk. The LLM has no ground source of truth, no database of facts, no way to even determine right from wrong. The knowledge it has is statistical and is distributed throughout its neural network. In these situations, where the stakes are pretty low unless you're a rabid Bulls fan, or the questions are pretty broad, like San Francisco activities, the statistical knowledge is sound enough, and you're probably going to be happy with the result. But the law is different, right? The stakes are high, and the questions tend to be precise, things like case law, precedent, jurisdiction, regulatory frameworks, so on, right? Due to the statistical nature of embedded knowledge, it is hard to predict whether you're going to get the right answer. So with high stakes and high precision, you really are rolling the dice when you rely on an LLM's embedded knowledge base. This is how hallucinations happen, and in our field, when they do, the consequences can be significant. So we want to stay away from use cases that rely on an LLM's embedded knowledge. Okay, so in summary, we love fluency in reasoning, we think creativity is valuable in the right doses, and we want to stay away from embedded knowledge. How does this translate to the product? Well, we lean into tasks that require fluency in reasoning, okay? For creativity, recall that there is a temperature lever that you can control. Well, we do control that lever. We turn it down for low creativity tasks like summarization, and up for high creativity tasks like connecting the dots to draft a statement of facts. Now, to minimize the chance of hallucinations, we want to avoid using an LLM's embedded knowledge. So we focus our tasks on the four corners of the document at hand, the evidence in your case, rather than more general purpose interactions that might rely on an LLM's embedded knowledge of the law, such as legal research. Because we include your evidence as part of the query during inference and not during training, the LLM does not have to reference it in the statistical fragmented way that it must store its own knowledge during training. It has full, high-fidelity access to the evidence at the time the question is asked, and is thus able to reliably cite and use that evidence. This careful design decision to focus on an LLM's strengths in our domain, so fluency in reasoning with the right dose of creativity, and to stay away from its weakness, embedded knowledge, allows us to provide a much more reliable experience for you with far fewer hallucinations. Still, these systems are not perfect. So we also think another critical part of building confidence is being able to verify their work for yourself. Okay, let's talk about verification. When I show people Everlaw's GenAI features, someone inevitably asks, but how do you know it didn't make any mistakes? Well, the answer is we don't. We don't know that. But perfection is the wrong standard to hold it to. Think about a hypothetical AI that detects cancer. If the goal is perfection, being 100% correct, it may never be released. But if the goal is to be as good as or better than humans, then lives can be saved as soon as the threshold is met and the AI is put into action. In our use case, the standard doesn't have to be saving lives or even better than you can do. It's something like good enough to save time and augment your work. I like to call it the smart intern standard. We think of it as a really smart intern that does work quickly to augment your own efforts. But just as you shouldn't blindly hand your intern's work in as your own, the same applies here. You want to verify the work that GenAI does and make it your own. So in our product design, we make that verification really easy for you to do. We get the AI to cite specific, immediately verifiable passages of text, page ranges, or Bates numbers from your evidence as justification for its responses. That way, you can check its work yourself, as you should. No one wants to have to explain to the judge that the intern did it. All right, that's enough talking. So let me explore these features in a live demo. Okay, so this is functionality that's actually on the Everlaw site today, and it's accessible by the users in our beta AI program. There's two classes of functionality here. One is around assisting review, making it more efficient, making it higher quality, and the other is on story building. All of them are consistent with our principles, right? They're embedded in the workflow, they rely on the four corners of the document, and they provide a way for you to validate or verify the results. So here, and the case we're using here is the Epic v. Apple antitrust case. It post-dates the training of these large language models, so they have no outside information about this case. unlike Enron, which they've learned about through Wikipedia and so on. And so here's a document. It's 9-page email thread. I can use our AI system to do all kinds of things to analyze this document. I can get a summary and so on. In this case, I might want to generate a topic summary here. And the AI is going to go read this whole 9-page document and generate some topics for me. And you can see here, I can read the topic and some descriptions. Okay, IAP test, relationship with Rob Caruso, fraud issue in Latin America. Okay, that's interesting to me. I want to learn more about this. I can jump to the area, the relevant area, again, so that I can verify this myself. You can see this fraud issue. There's a bullet point right there, fraud in Latin America, a paragraph about this kind of fraud, right? Okay, so that's one bullet point in a 9-page email. I might have missed that myself, but the AI can help surface that kind of information for me. Let's see what else it can do. Okay, so here is a Senate Judiciary Committee transcript. It's 57 pages long. The AI can generate people and organization summaries, so the specific people and a little bit of information it's garnered about who they are in the context of this document. So you can go jump in and understand the key players here. You can also dig a little deeper in documents. So this is an iOS developer program license agreement. It's 50 pages long. I can honestly say, as a consumer who's not a lawyer, I have never, ever read an entire license agreement myself. And I don't envy the poor reviewer that has to slog through these 50 pages to find the critical information that's probably very valuable in this antitrust case. Or they could use the AI, right? So you can actually ask a question. So, under what circumstances can Apple terminate this agreement, right? And so the AI is going to read through this document bit by bit and actually try to find out the answer to this question for you, right? So you can see here it's going chunk by chunk, pages 1 to 4. It can't find anything about termination, pages 5 to 7, similar. But eventually, you will get to a point where it finds some good answers. You can see here pages 18 to 20. According to the text, Apple can terminate its agreement under the following circumstances and a whole bunch of reasons, right? But of course, you can then jump right to pages 18 to 20 yourself and see what the document has to say. Here we can see, section 8's about revocation, and there's a bunch of reasons here, right? So again, it can really save you that time and give you insight into the document. And you'll notice that, I asked about termination. The actual language here is about revocation. The large language model is smart enough to realize that these are, related terms. Okay, so that's some of the features around augmenting and assisting review. Let's switch over to the storybuilder side of things. So as a reminder for folks, review is about taking a haystack of 1 million documents and finding that 200 or so needles, right? Storybuilder is about taking those 200 needles and telling a story with them, right? So it's a different kind of use case, but really, really important for downstream post-review tasks. It has a bunch of functionality, timeline tool and depositions and all that other stuff. So imagine you're an attorney coming into the case at this stage, right? There's 100 documents that your reviewers have surfaced as really hot, right? Your job is now to synthesize all the information in these documents to tell a story, to figure out what's going on. What's our best argument, right? That's hard to do. Now, you can start by using these nice AI-generated summaries that we've done for you. That's a nice benefit, right, of this new technology. All these summaries that you can see by the little 3 stars here generated by the AI. But even then, 100 summaries in your head, that's going to take a lot of time and effort. You might miss some things, right? So instead, you can ask the AI. Let's make a new draft here. So drafts are our real-time collaborative writing tool. You can write and work on documents with other people. You can actually inject evidence inline into the text you're writing. Let's say I want to generate a statement of facts here. I'm going to ask the AI to do this for me. I might just say at a very high level, focus on antitrust and consult any or all of the evidence in my story, those 100 documents. Now it's going to go to work consuming those 100 summaries and metadata and synthesizing that information. It's going to take a little while, maybe 40 seconds to a minute. It's got to do a lot of work there. But it's going to generate something. And by the way, it knows nothing else about this case. It has no outside context other than those documents. And it will generate something different every time. I don't know what it's going to do now, but I found, generally speaking, it's quite good at doing this. And you can ask it lots of other kinds of questions. You can say, focus on Tim Cook. What's Tim Cook's role in all of this? And it'll do that. You can say, based on the same evidence, what will opposing counsel say? What are their counter-arguments to what we might say based on the same set of 100 documents? So those are all the things. You can kind of, sky's the limit here in terms of how you want to interpret stuff. But here you go. This is now generating information. The text is a little small here, but if you're familiar with this case, you can try to read it and see whether it holds up. Epic Games, a leading video developer, and Apple, a multinational technology company, are engaged in a legal dispute in the United States District Court, blah, blah, blah. And it's actually citing evidence that you can go verify for yourself. And ultimately, you can make this document your own, as you should, and use it to augment and improve the quality of your work. And you can see it kind of lays out point by point a narrative story of what's going on and the key players, the key issues at hand, which is, I think we find really, really impressive. So these are some of the things that you can do in the platform. And we also, the reason we have a beta program is because we can test this. We have tested this on our own data sets, which it does quite well on. Our beta users are now testing this on live case data, and there's no better way to assess this technology than putting it to the test that way. Thank you, and enjoy the rest of the conference.